Let's do another carbonyl nucleophilic addition reaction that actually forms a new carbon-carbon bond. And it's interesting, this reaction, the Wittig reaction here, the new bond is a CC double bond. So the Grignard reaction made a CC single bond with an OH attached, right? The Wittig reaction will make a double bond. So let's start with a primary alkyl halide right here. This is just methyl bromide. This is actually better than primary, so we could have ethyl or something like that, but primary or better, alkyl halide. Triphenylphosphine, 3 phenyl groups attached to a phosphorus, right? P is under nitrogen on the periodic table, so it does something similar. It has 1 lone pair that's a nucleophile. Okay? We essentially alkylate this phosphorus by SN2 displacement. So we have P plus, right? P with 4 bonds is a plus, just like nitrogen with 4 bonds. Here's the R group that came from the alkyl halide. Now we need to take some sort of strong base, right? N-butyllithium, right? CH3, CH2, 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 Li. That reacts like a carbanion, right? Where it's a C minus. So just like a Grignard reagent, essentially. So an alkyl lithium is another C minus. Okay? This is a very strong base, pretty much the strongest. I mean, we got sec-butyllithium and T-butyllithium that are a little bit stronger, but N-butyllithium here is the workhorse extra strong base that's used in many, many organic reactions. We're going to see it from time to time. So butyllithium, very strong base, deprotonates one of those hydrogens. What we end up with is called a ylide. Where I have a C minus next to a P plus. Okay? A compound that has adjacent positive and negative charges is in general called a ylide. But the reason we can have that is that C minus there is that those 2 electrons can actually donate into that phosphorus right there, and phosphorus can expand its octet, and then that charge can be distributed through those benzene rings. Okay? So this is a stabilized C minus, essentially. So what can happen then, the ylide, right, here's our ylide, 2 R's, or however many R's we need to have on that C minus, with the PPH3 plus next to it. Okay? Nucleophilic negative carbon adds to the carbonyl, right, if we have some other carbonyl compound. That forms a new CC bond. Okay? The O minus forms a bond with that P plus that's just right next to it, forming this really interesting 4-membered ring that has C, C, O, and P in it. What happens then, spontaneously, this 4-membered ring collapses, right? The CO electrons go to make PO double bond. The PC electrons go to make a CC double bond. So that ring collapses, making a CC double bond, okay, breaking those 2 other bonds and making triphenylphosphine oxide, PH3P double bond O. So this, what we've formed here, is a new CC double bond, right? So if we look at this retrosynthetically, which we'll do on the next page, what we look at is that if our product has a CC double bond, we can form that CC double bond, right, 1/2 to the other with a Wittig reaction. So let's look at this a little more practical terms here. Triphenylphosphine really only adds to primary alkyl halides. Really only does it well anyway. We could make it work with a secondary. It would be slow, but primary is the most practical. So that means that looking at our product that we need to have here, the mono-substituted side of the final double bond has to come from the ylide. It has to come from that phosphorus part. Okay? Let's sort of think backwards a little bit here. If this mono-substituted side came from this compound right here, that would have to come from the triphenylphosphine, PH3P, and some sort of, do we use bromides mostly? Yeah. Right. Bromine, CH2, CH3, something like that. Okay. So this attacks, displaces the bromine, then we deprotonate it, right? It's really 2 steps. Okay. But if you just look at the carbon skeleton, right, this carbon just has one R group attached to it, right? This CH3 right here becomes that CH3. Okay. We only have one R group right there. And that's important for a Wittig reaction to work well. Okay, so let's start with one that actually doesn't matter quite as much, but there is one way that'll work a little bit faster than another. So if this is our target, and we want to retrosynthetically decide how to make this compound, well, the last thing we'll be doing is making that CC double bond via the Wittig reaction. Now, whatever side has fewer R groups on it is going to be the side that comes from the yllid, right? Here we actually have a mono substituted and then a non-substituted, right? We have a CH2 on that double bond. So the best way to do this one would be to have the carbonyl, right, on the side with the R group. The other part will be the yllid, PH3P plus CH2 minus. Okay, so just recreate this side of it, okay, but call that a C minus. Okay, recreate this other side, but make that into a carbonyl. Okay, that's how we break down the Wittig reaction, going retrosynthetically. And then in the forward direction, let's do this whole thing. Okay, all I need is CH3 methyl bromide and triphenylphosphine. That'll give us PH3P plus CH3 right? Then we need N-butyllithium, right, which is a base that will deprotonate that carbon there, giving us PH3P CH2 minus. Okay. That can react with the carbonyl that we had, so cyclohexane carbaldehyde. Here, I'll just draw that same direction, doesn't matter. What that's going to do is give us this alkene. So if you ever have a carbonyl that you want to make into a terminal alkene like that, replace that O with a CH2, we use the CH2 Wittig reagent, CH2 minus PH3P plus. All right, if this compound is our target, we have a di-substituted side of the double bond and a mono substituted side of the double bond. So going backwards retrosynthetically, the side with more R groups will be the carbonyl. So benzene, CH3. So this is acetophenone. Okay. The other side will be our yllid, PH3P plus. This carbon has just one hydrogen, so the yllid will be the same, CH minus, and then benzene. Okay. Forward reaction, I need benzyl bromide. So benzene, CH2Br. React that with triphenylphosphine. We get CH3P plus CH2. Benzene ring. N-butyllithium will deprotonate. pH3P plus CH benzene. There is our ylid. I'll add that to our carbonyl, acetophenone. We get our product. Where the carbonyl was is now a double bond, and then we pick up with this carbon. There's a CH, there's benzene. Remember, retrosynthetically, if I want a terminal alkyne like that, what I've drawn here is pretty much like acetone, but with CC double bond instead of CO double bond. That comes from acetone plus pH3P plus CH2 minus. That's an important retrosynthetic tool for you to have. If you ever need to make this kind of terminal alkyne, make it from a carbonyl and the Wittig reaction.